Greetings, scientists. Before we get into the maths of calculating density, let's first of all explore what we mean by density. So density is basically a measure of the amount of stuff that we can pack into a fixed unit of volume. And it's at this point that a curious science student would ask, why is this important? Why is it useful to measure density? Well, a couple of reasons. Number one is by measuring the density of a solid, it helps us learn more about the properties of the matter in that solid. And second of all, we can determine whether it will float in a liquid. Because if we take this cork, for instance, it has a lower density than the water that we've placed it in, the liquid that we've placed it in, hence it will float. Whereas this aluminium has a higher level of density compared to the water that we place it in, so therefore it will sink. Now, the good news for density is there is a simple formula that enables us to calculate density. So students, if you are being tested on this, I would be asking your teacher if you are going to be provided with a formula sheet, or do you need to memorize it? If you need to memorize it, just remember that D equals M over V. Now, be very careful with your units of measurement. If we're dealing with relatively light objects, then we're going to be working with grams and centimeters cubed. Heavier objects, we're going to work with kilograms and meters cubed. If we're working with liquids, we're going to be working with milliliters or liters. We can work with bigger or smaller units, but generally in Year 8 science, we're going to be working with grams and kilograms or centimeters and meters. Be very careful with this. We might need to work with decimals. You might need to do some conversions of meters to kilometers or grams to kilograms. So always best to show your workings out on this when solving some type of assessment task. So in terms of our formula, our numerator is mass. What is mass? The mass is the amount of matter that we can pack into an object. These are the particles, the atoms, etc. Students traditionally get mass and weight confused. So yes, we measure mass on scales and we get a reading in grams and kilograms, but that's not the same as weight, because weight, we need to factor in the gravitational field strength, and that varies depending on what planet or star or asteroid that we're on, but let's save that for another video. So the denominator of our formula is volume. Volume is how much space is taken up by the object. In this video, I am focusing on calculating the density of what we call regular shaped objects. So whether that be a cube, some type of prism, a cone, a cylinder, a sphere, a pyramid, etc. We can clearly measure length, width, height, radius, and then we can apply a formula to work out the volume, which, remember, is the denominator for calculating density. Now, if the object does not have a regular shape, we can't use a formula to calculate the volume. And that's when we've got to come up with an alternative method to calculate the volume. We can still measure its mass, we can put it on the scales, but what we need to do is potentially do something like the water displacement method. Now, I'm going to cover that in a separate video to keep this video short and sweet. So let's have a go at some examples. So in terms of these three objects, we can see that they've all got the same volume. So they've obviously got a length of 1 centimetre, they've got a width of 1 centimetre, and they've got a height of 1 centimetre. So volume equals length by width, L by W by height, which is 1 by 1 by 1, which equals 1 centimetre cubed. That's what we have for all three volumes. The masses vary. When we put these cubes on scales, we come up with different measurements. So you'll always get credit for putting in the formula. So start with your calculation, D equals M over V. So for our foam here, be careful with your decimals. We've got 0.03 as our mass. Our volume is 1. And then we just get an answer of 0.03. Now be very careful with your units. So therefore that's 0.3 grams per centimetre cubed. Let's go with our diamond. I've made a bit of a mess here, but anyway, let's persist. So again, the mass of our diamond, our numerator, is 3.5 grams. We've got a volume of 1, so a nice easy calculation here. I'll just put that in there. Means we've got 3.5 over 1 equals 3.5 grams per centimetre cubed. And if we did the iron one, we'd come up with an answer of 7.8 grams per centimetre cubed. Okay, let's do something that's a bit more mathy. So again, I'm going to do this. I'm going to start by working out the volume. So the volume of a sphere, if we go back a few slides, the volume equals 4 over 3 pi times r cubed. So 4 over 3 on your calculator, if we work that out, that's 1.33 recurring times pi. I'm just going to go to 3 decimal places with pi 3.143. And radius is 5, so we go 5 cubed, 5 squared is 25, 25 times another 5 is 125. All right, so on your calculator, 1.33 times 3.143 times 125 equals 522.5 centimetres cubed. So step 2, put in the formula for density. E equals M over V. Okay, so now we need to be careful here because we've got some units issues. So 1 kilogram, kilo means 1,000 kg. We've got to convert that into grams. So otherwise we're going to make a massive error. So kilo means 1,000, so that means we've got 1,000 grams in this sphere. So therefore in our calculation, our numerator is 1,000. We divide that by our volume, which we worked out before, right here, 522.5. And then I'm just going to grab my phone here because I can't work that out in my head. So 1,000 divided by 522.5 equals, I'll go to 2 decimal places, 1.91. Again, careful with your units, grams per centimetres cubed.